Good afternoon, everybody. It is still Wednesday, September the 13th, 2023. We're still at the University of Linkoping, and I am still teaching. This is the second lecture, part of this mini course here in Linkoping. So I was extolling the virtues of these pairings as operations that, for all intents and purposes, work like inner products. And so in what follows today and tomorrow, I will show you a few proofs, and I will use for the proofs, I will use these properties. I will use subadditivity in the first argument. So you have the first argument, and then you bring them out, but it's subadditive, which means that it is less than or equal to. And then I will have Cauchy-Schwarz, I will have positive definiteness, and sometimes, but less often, homogeneity. All right. So, and we have seen this was in the context of the continuous time Banach contraction theorem, and which is really justified, which really justifies this relatively unusual notion of one-sided Lipschitz constant, because we're all familiar with the Lipschitz constant, and this one is the one-sided version of it. All right, so my task is I would like to elaborate on this topic right now, and maybe fill out a few gaps. So, but the main idea was the continuous time Banach contraction theorem, which I did, and then we'll take a break. So, first off, in the literature, people have studied contractivity, as I mentioned to you, for 50 years, using different names, different symbols, different norms, and so on and so forth. So in this table here on these slides, there are 9 entries, and I can find papers in the literature about each one, essentially each one of the 9 entries, independently, without understanding which one is which and why, and so on and so forth. So let me clarify. So remember, I gave you those 2 conditions, wasn't it? Right? One was that the one-sided Lipschitz constant, it's either the infimum over all B such that something happens, or it's the supremum of the log norm of the Jacobian, right? There are the 2 equivalent conditions. Maybe I would like to call the first one the integral condition, because I don't take any derivatives. And the other one, I'll call it the derivative condition, right? Because I take derivatives. This condition here was the inner product fx minus fy into x minus y less than equal than b times x minus y squared. Also, I mentioned to you in the previous lecture that when you want the log norm to be less than a constant, for example, I can rewrite that, right, as an LMI. Remember I had those cases? Allow me to briefly show this back to you and remind you. I showed to you that in discrete time, I can rewrite the 2 norm as an LMI, and the infinity norm being below a number, I can rewrite it as a linear program, right? This was in discrete time, but the same is true in continuous time as well, right? We discussed this earlier, that I can rewrite log norm conditions into LMI. Well, for 2 norms, for weighted 2 norms, and for weighted infinity norms, I can rewrite them as linear programs. There's actually a whole theory of why is it possible to go from log norms to this type of, let me call these generalized quadratic inequalities for a second, just a big name. But in any case, there are equivalent translation. That's why that table has 9 entries. Let's go back now to the table, because I can write the condition which asks for the log norm of the Jacobian to be below a certain number. So that's one set of conditions. I could do it for the 2 norm, the 1 norm, or the infinity norm. Then I can write the integral condition where I do not take Jacobians. This would be, this condition here is exactly this one here, right? I'm writing the inner product is less than equal than the fx minus fy into x minus y. Here I wrote it in a different order. I apologize, but it's the same, right? So this inner product is upper bounded by that. This weird inner product, which is the pairing, is less than that, or this other weird inner product, which is the pairing for the infinity norm, is less than that. So you see that these three are the integral condition for the one-sided Lipschitz constant less than b, or the log norm less than b, or these generalized quadratic inequalities, which for this table I'm just going to call it the Demidovich condition, and this is an LMI in the case of two norm, or these other weird conditions for the one and infinity norm. So that's why there are 9 conditions: two norm, one norm, infinity norm, and then I have integral condition, log norm condition, or this equivalent transcription, which is possible. Now, that's one way to put it. So let me just try to talk just a tiny bit about this Demidovich condition. So this one, what does this condition say? And let me actually do this. So this is the Jacobian, this is the Jacobian, right? Right. So this condition is saying, if you want to prove contractivity for me, go find a positive definite matrix P such that P times the Jacobian plus the Jacobian transpose times P is negative definite. And specifically, you can find a negative number P, making this in LMI hold true. And this LMI has to hold for all x's. For all x's, this LMI must hold, and B must be negative. If B is negative, I'll call that minus C, and C will be the contraction rate. So this is the contractivity LMI, but it needs to hold everywhere in space. And so that's why this is called the Demidovich condition from the 1961 work by Demidovich. It's also referred to as the let us find a common Lyapunov function problem, because put the right-hand side to 0 and use a quadratic Lyapunov function of the form 1/2 x transpose px. Then this is just the derivative of this is going to be appearing in the derivative of the Lyapunov function, and you need the same p to work everywhere in space as a function of x. So right now I skipped a few steps, but just to give you an intuition. The Demidovich condition, right? These conditions are equivalent. So even the full equivalence, I don't know. Let me just erase the table and start another comment. Even just the fact that these 3 conditions are equivalent is not widely understood. It is not widely understood. So there is a body of work on synchronization in nonlinear dynamical system, which uses something called the quad condition, and they were using this condition for the longest time. And then the equivalence between the quad condition, which I'm calling one-sided Lipschitz condition, and the Demidovich inequality LMI has become apparent and clear only recently. Over the years, the papers on compartmental systems, on neural networks, and on traffic problems have realized that the one norm is quite appropriate, because for neural networks, I'll talk also about the infinity norm. But in certain systems where there is a conserved quantity, the one norm is particularly well suited for reasons that I will clarify later. And so these conditions have appeared in that literature on traffic and on compartmental systems. All right.
Question.
Yeah.
Ranser wrote in something called density functions.
Yes.
Is that connected to some of the columns here? Or?
I am not sure it is connected. because the concept of a density function has a relationship with Lyapunov functions, and I will show you the Lyapunov functions that arise here. What may be true is that a strongly contracting vector field with respect to any one of these norms have Lyapunov functions, which I'll show you, and they themselves can be written as density functions in an appropriate transformation. I haven't had the time or the opportunity to do so. Right. I have not shown to you the Lyapunov functions that arise from this, so I need to show you what Lyapunov function will come out. All right, let's remember that. All right, so let me proceed. Let me tell you a little story. Right now, I'm not just telling you the story. So why am I so interested in doing this generalized theory, which handles not only the 2 norm, but also the infinity norm and the 1 norm and other cases? So I will tell you a cute little story. It's also a little tribute to Boris Polyak, who's a mathematician and optimization scientist who passed away this year. So it's a nice little touch. And he used to say, I've seen a talk by him on YouTube, he used to say that Rn contradicts our intuition. So you have intuition about things in large dimensions. Your intuition about geometry will lead you to the wrong belief. So I have a picture here. This picture illustrates a trajectory of a dynamical system in large dimension, which I projected onto a 2-dimensional plane. Otherwise, because of existence in uniqueness of solution, trajectories would not intersect, right? And I want to study the practical stability problem. By practical stability, control theoreticians mean to say, I want to know that there exists a neighborhood that after some time I'm going to be inside that neighborhood. And I would like to compute or estimate the settling time. So my aim is to compute the settling time to get inside the desired set. I want to get to that set. How long time will it take me? All right, but norms in Rn are equivalent. I should define this. This is a useful concept, which I will show you something like this, right? So suppose I take 2 norms in Rn. I take 2 norms. Right now I'm using alpha and beta for my 2 norms. It turns out that there always exist numbers, positive numbers greater than 1, kappa alpha beta and kappa beta alpha, such that for all x, that the following is true. You can upper bound the alpha norm by the beta norm, and you can upper bound the beta norm by the alpha norm, and you put these coefficients so either my convention is beta lower is upper there, almost simplifies, and I remain with alpha. Anyway, it's just a little convention. And I think I misspoke. I said that they're greater than 1. It's not true they're greater than 1. What is greater than 1 is the product. This product is always greater or equal to 1, typically greater than 1. All right. Right. It's equal to 1 if and only if the 2 norms are identical. All right, fine. So another way to think about it, if you take the unit ball of one norm, and then let's say it's a circle, and then the unit ball of the other norm is a cube, you can always fit a larger cube and a smaller cube inside, and the factor is, you can compute what the conversion factors are. It's fine. So the norm are all equivalent, right? Because you can always go from one ball to the other ball with upper bounding. So what's the big deal? Since the norms are equivalent, if I'm interested in settling time, it really should not make any difference which norm I use, right? It doesn't matter. You use Francesco, measure your ball in the 2 norm or measure it in the infinity norm. Okay, let's make 2 assumptions. Will you decide whether you like my assumptions or not? I will make 2 of them. The first assumption is that I'm willing to tolerate an error in each coordinate. Let's say size 1 for the conversation. So I'm okay if every coordinate is off by a fixed amount. Now, what that means is that my desired set where I want to end up with in every coordinate, I want to end up with a small error. So my desired set is a hypercube, right? Because I tolerate an error in the x, tolerate an error in the y, I tolerate an error in the z. This is going to be a hypercube, which is the unit ball for the infinity norm. Okay. Now let's suppose that you are a traditional, control theoretician. You're going to use a quadratic Lyapunov function. And right now, you should be looking for a P matrix so that it is a weighted 2 norm. But for now, let me just use unweighted. So it's just your Lyapunov function is just x, the 2 norm of x, the 2 norm of x. So now, if these two assumptions hold, then let me notice for you that you need to wait. If you want to compute the settling time, you need to wait until the solution enters the unit 2 ball, because if you want to make sure that, that the unit 2 ball is inside the unit L infinity ball. And if you want to be sure that every coordinate has an error plus or minus 1, that means that the 2 norm has to be upper bounded by 1. So you want to get into a box, you want to get into a cube, and you need to look for the level sets so that the sphere is inside the cube. Because if the sphere is outside the cube, then you're not inside the cube, right? You need to make sure that you go inside the sphere, which is inside the cube. Does that make sense? So, fine. That's not a problem, right? Because if you look at this picture, the sphere in 2 dimensions is almost as big as the square in 2 dimensions. What about 3, 4, 5, and more? I've got news for you. Here's what Boris would tell you. He would say, if he was here, that the n sphere inscribed in the n hypercube is a very small fraction of the hypercube. Very small. So small that the ratio of the 2 volumes, so if you divide the volume of the hypersphere by the volume of the hypercube, that number goes to 0 faster than any exponential function. So it's not even exponential, it's faster than exponential. And so the punchline is that in large dimensions, the quadratic Lyapunov function may provide exponentially conservative estimates of settling time. For example, I played with settling time, but there could be other things. Yes. All right, this was my cute little story about Boris Polyak's observation. There are other reasons, as I was telling you, and I shall show it to you later. L1 norms are very appropriate for monotone, for certain classes of systems which conserve quantities. Also, you have already heard it from me. Linear programs are more scalable than LMIs. So if you have a large scale system, and it doesn't always happens to be the case, but if you are able to analyze it using L1 or L infinity norms, then calculations are typically going to be linear programs, just like Professor Ranzer would say, and those are much more scalable than LMIs, and so on and so forth. Even in machine learning, this example I mentioned here, in machine learning, adversarial attacks are better modeled with the L infinity norm than the L2 norm. If you're interested, I can give you a reference. This is really ultimately the same as, very closely related to the Polyak example in the next slide. And it has to do with the amount of how do you measure the perturbations. And finally, I will mention that, I'm not going to cover it, but in 1981, Bertsikas proved the theorem about the fact that if you have a contraction mapping, imagine you have a contraction in Rn, so you have n variables, and you have to update n variables. Now, imagine that each variable is associated to a different computer. So now you have n computers. Each computer number 1 has variable number 1. Computer number 2 has variable number 2, all the way to n. So now, computer number I needs to apply t in order to compute the next value, right? So what does it apply? It needs to apply t sub I, because the map t maps Rn into Rn. So if you want to update a value I, you need to compute ti. And Ti will depend upon your state. Imagine you are agent number I. So Ti will depend upon your state, and it will depend upon the other states. So the fully asynchronous execution model is defined like this. Computers talk to each other at randomly selected times with arbitrary delays, and the communication may fail as well. So T is a contraction. So the contraction factor, the Lipschitz constant of T is less than 1. When is it true that my contraction map executed in the totally asynchronous model will still converge, despite the fact that when processor I updates its state, xi, it will use outdated information about all of the other processors. So that's the question. And the theorem that, if you're interested, we can discuss, but I don't have slides for, is that that is going to work only when the norm is the infinity norm. It does not work for other norms. Okay, perfect. In the slides, you can find all of these references about other papers that use non-Euclidean norms to prove various properties.
Good question.
Yeah.
Computational advantages.
Yeah.
Is it always possible to derive an LP with a fixed size, regardless of any kind of choice of position or anything?
Is it always possible to
derive an LP with a like a predefined size, which has no conservative approximation?
It is always so you can give me for example, let's take it super simple. I give you could take a matrix. You give me a matrix, I can check if it is contracting with respect to the infinity norm, and that it may or it may not be. I can also use a diagonally weighted L infinity norm with an eta, had an eta parameter, and that may help. It may be Hurwitz, it may not be Hurwitz. If the matrix is Metzler to begin with, so if I have a positive system, then by using an infinity norm, I don't do, it's not conservative. But if you give me an arbitrary sparse matrix of dimension 1 billion by 1 billion, stored in a very sparse manner, and now you ask me to find out if it is Hurwitz or if it is contracting, I can easily check with the infinity norm, but it's going to be conservative. I think I'm not sure I expressed myself well. Maybe we can take this offline. Yeah. All right. Let's see what else I got for you here. I have some proofs. I would like to prove a few things, or at least give you a few ideas of how do you prove these things, just because it adds a little bit of depth. Because I have made many statements about the continuous time Banach contraction theorem, and I did not prove any of them. I just blurbed them out. So let me just prove a few things for you. So the first, and also because I want to show you how to use these pairings, just in case you ever get a chance to use them. But it'll be fast. It should not be too difficult. So first of all, and I made my purple darker during the lunch break. So how do I prove the continuous time Banach contraction theorem? Why is it true? The one-sided Lipschitz constant being less than 0 implies that there exists a unique globally exponentially stable solution, and all the trajectory converge to each other with the rate c. It's very, very simple. And it's precisely the curve norm derivative formula. What was the curve norm derivative formula saying? It was saying that if I take the time derivative, but I have to write it with respect to this Dini derivative because it may be only locally Lipschitz, but please do not worry about that. Of x of t, for example, squared, well, that's equal to the norm of x of t, which multiplies the Dini derivative of that. And this is equal to the pairing between x dot and of, I should say, of t and x of t. This is precisely the curve norm derivative formula, which Remember, I drove you a little bit crazy and I said to you, I'm going to give it a name because it doesn't usually have a name, but okay. So now I apply this formula not to a single curve x of t, but to the difference between two curves. But of course it works. It's as if here this was z, 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 and it's just a difference as z is equal to x minus y. So it's the same, right? And so this equality sign here is exactly the curve norm derivative formula. It tells you that you need to take x dot minus y dot into x minus y. That's the derivative of the norm. But x dot is equal to f of x, y dot is equal to f of y. This is exactly f of x minus f of y into x minus y. And this is exactly minus c norm of x minus y squared, because that's exactly the one-sided Lipschitz property, right? You remember the one-sided Lipschitz property was fx minus fy into x minus y less than equal than b times x minus y squared. And now as b, I'm assuming minus c. Right? And by the way, sometimes I write fx because I'm lazy and I should write f of x, right? So this is exactly it, right? So now I have obtained the fact that what did I obtain? The one copy of the norm times the time derivative of the norm is upper bound of minus c, 2 copies of the norm. So I eliminate the square with that factor, and I obtain this differential inequality. Does that make sense? This differential inequality says that the distance between the two trajectories x and y is decreasing. Well, decreasing for sure because the right-hand side is negative. Because this is a norm, so it's not negative, and c is positive, so it's decreasing. And essentially, the next thing you can use the ground-wall comparison lemma. The ground-wall comparison lemma tells you that the solution of this differential inequality is upper bounded by the solution of the differential equality. And we need to just write down, there's a proof in 2 slides for now, but in any case, this is an inequality, but the solution is upper bounded to the equality. And the solution to this equality is, of course, that the error at time t decreases, well, it's upper bounded by e to the minus ct, the error at time 0, the distance between the trajectories at time 0. And so therefore, for any time you select strictly positive, for example, time equal to 1, but in reality, any positive t, the product between c and t will be positive, minus that will be negative, and e to the negative number is always strictly less than 1. Therefore, for any time you fix, I have now shown to you that if you flow from x naught y naught to x of t y of t, the distance between them must have decreased. So I have shown to you that, for example, at unit time, the flow map is a contraction with contraction is a discrete time contraction with the contraction factor equal to e to the minus c. The rest is an application of the discrete time Banach contraction theorem. It goes like this. So Rn is a complete metric space. But then the Banach contraction theorem implies that there exists a unique x star, which is a fixed point of phi. Most people stop here, but the proof needs another observation. So essentially, I have shown to you that the one-time flow map has a fixed point. Now, some people will say, "Oh, I'm done. It's an equilibrium." Well, to be careful. Phi of x star equal to x star implies that either x star is an equilibrium of phi, or x star is a point in a periodic orbit with period 1 for the ODE. Now, it's easy to see by contradiction that the second case cannot be true, and therefore I prove for you that there exists a unique equilibrium to which all trajectories converge. So this is my proof of the Banach contraction theorem in continuous time. Any questions? Here, I'm not sure I want to go over this, but let me just mention, in the book, you can find more details if you ever need them or if you are interested in them. You are differentiating the norm of the curve, and when the norm is not Euclidean, then the norm of the curve is not differentiable everywhere. It's locally Lipschitz, as I was telling you. So then you need to define a better, you need to use a better notion of time derivative. And so the right notion is to use something called the upper right Dini derivative. It turns out there are 4 Dini derivatives, the upper right, upper left, lower right, lower left. We only need one of them. And of the all properties that Dini derivatives have, you really just need this. If you're given a continuous function, if the Dini derivative, the upper right Dini derivative is non-positive, then the function is non-increasing. If the Dini derivative is strictly negative, then the function is strictly decreasing, and so on and so forth. And by the way, at any time where the function is differentiable, the upper right Dini derivative is equal to the standard time derivative. So essentially, you're essentially using this Dini derivative exactly the same way in which you would use the standard time derivative. And now here, this I wrote for you also the Grunwald comparison lemma. See, Grunwald did this long before Bellman, but it's now known to be gotten to be called Bellman-Grunwald lemma, the Bellman-Grunwald comparison lemma. I think it's not fair because Grunwald did it much earlier, but in any case, then you should call the Banach contraction theorem, you should call it the Picard-Banach-Cacciopoli contraction theorem to be fully consistent. But in any case, all right. So you have, and it works also with the Dini derivative. It doesn't need to be right. Okay. Finally, I would like to remind you of something you already may remember, and show you how to generalize it in the case we're in. So. What you should remember is that you define the Lipschitz constant of a map. The Lipschitz constant of a map, well, it's the infimum, right, of a number L such that fx minus fy norm is upper bounded by L x minus y for all x and y, right? This is the definition of the Lipschitz constant without using derivatives. And then if the map is differentiable, it turns out that the Lipschitz constant can be written using these 3 operations. First, you take the Jacobian, then you take the norm, then you norm, and then you take the supreme. Why is this equality sign true? Do you remember your multivariable calculus? How do you prove that the integral definition, I'm using this language, right? They call it the integral because I'm not doing any derivative. But this definition is the same as the derivative definition, if you want to call it, because sometimes people define it directly like that, which is the supremum of the induced norm of the Jacobian. Why would that be true? You need to show that 2 quantities are equal to each other. So here's the way I'm going to do it. I'm going to make 2 observations. Well, I'm going to do is, so earlier I said this is true and I should remember it. And then in this mini course, we are seeing that this is also true, right? So this is the standard equality. And then the point that I am making for you today is that if you define the one-sided Lipschitz constants with the pairings, then it's equal to the supremum of the log norm of the Jacobian. So how do I prove both equalities? Essentially, the proof method is more or less the same. Mind as well, I do it for the new case, the one on the right, because it's new, it's kind of fun. Let's see it in action. So I am going to show that the one-sided Lipschitz constant is upper bounded by the supremum, and then magically I will make it appear here your converse inequality. The supremum is upper bounded by the one-sided Lipschitz constant. Does that make sense? So if I want to show 2 quantities are equal, first I show that the first quantity is less than equal than the other, and then I show the converse, and then I'm done. So one direction, intuitively, one direction is going from the function to, from the derivative of the function to the function. And for that, you use the mean value theorem. if you have information about the derivative of a vector valued function and you wish to infer properties of the function, you can use the mean value theorem. But for vector valued functions, so make sure you use the right statement. If instead you have information about the integral version and you want to know something about the derivative, then what you're going to do is going to take f of x plus h, subtract f of x, divide by h, and let h go to 0. And that's going to give information about the derivative, right? All right. So here, allow me to just show you. This is the correct statement of the vector value of the main value theorem for vector valued functions. So I'm going to plug it in. I'm going to enlarge this a tiny bit. So the one-sided Lipschitz constant is equal to f of x minus f of y. But f of x minus f of y gets to be this entire thing because of the mean value theorem. Then, now I have an integral inside the operation, but the operation is sub-additive in precisely the first argument, not the second. But I have a summation of things in the first argument. So this inequality here is precisely the sub-additivity property of the pairing. And now I bring the pairing inside, right? Does that make sense? Then what do? I forget. I don't remember anymore. Oh yeah, I've got a supremum outside, and the way that inequalities work is that if you take the supremum of the integral of a quantity, it's upper bounded by the integral of the pointwise supremum, because the pointwise supremum is going to be, of course, larger than the supremum when you take it outside, right? And now, magically, here I'm just changing variable. So this equality sign is just a change of variable. I go from xy to yz, nothing to worry about. And then notice that I end up having the numerical range. So I end up having a matrix that multiplies a vector paired with a vector, and I worry about the worst case value of that. And I don't know if you remember, but this was what I called the Lumer equality a little while back. And so when you plug everything in and you do the calculation, you have proved one direction of the equality sign. So mean value theorem and manipulations using the properties of log norm, induced norm, or the pairing. Now, the other inequality is, well, as you remember, the Jacobian of f is equal to the Jacobian of f dot v. So in the direction of v, the Jacobian of f at the point y, and you write a formula for it, which is just a limit formula for what the derivative is. And then maybe I will skip this. It's basically bracket. So the yeah, you need to play carefully with the way in which you choose x and y. And then you write a definition of one-sided Lipschitz constant, which will involve f of x minus f of y. You plug in the values of x and y, specifically that x be y plus hv. In this particular case, you use weak homogeneity. You will use again the Lumer equality, and you use one more thing. Remember I told you about the axiomatic properties of this pairing? It turns out that you can prove that the map from any vector to the paired vector w into v is a continuous function of the first argument. And so this makes the whole proof comes true in the end. I'm scared of looking at you. I hope I did not make it too boring. All right. Okay. I've spoken for 40 minutes. Let me now finish the first and essentially also the second part. I would like to make a point here. We have discovered that induced norms and induced log norms are very important in contraction theory over vector spaces, over finite dimensional vector spaces, because essentially, oftentimes you're going to have a dynamical system. You look at its Jacobian and you try to see if you can prove that the log norm of the Jacobian is always negative. That's the name of the game. Maybe you rewrite it as a linear program. Maybe you rewrite it as a as an LMI. Maybe you write the integral version. Okay, in the integral version, you don't have the log norm, but oftentimes you have the log norm. So if you really want to apply this theory, you need to get your hands dirty and study linear algebra. There's something nice about this aspect of contraction theory, because basically all of the nonlinearity ends up in the structure of the Jacobian, and then you decouple that, and now you can just study all of the properties of log norms of matrices. You can study log norms on just matrices, understand the structure of that, and then you're going to plug in the nonlinearities. So in this a little bit crowded slide, I wanted to make the case that Lipschitz constants and matrix norms are very, very similar to each other, and they have the same sets of properties that the modulus of a complex number would have. So if you take the modulus of a complex number, it's non-negative and it's equal to 0 only when, if and only if the complex number is equal to 0. If you multiply a complex number by a scalar a, you bring out the a, you get the absolute value of it. If you sum two complex numbers and you take the modulus, that's upper bounded by the sum of the modulus. And if you mold the product, then the product of the complex numbers is equal in that case, but upper bounded are equal by the product of the modulus. And these same properties hold for the Lipschitz constant as well. If instead you are working in continuous time and you are looking therefore at this crazy new operation that I introduced for you today, the log norm, or even crazier, the one-sided Lipschitz constant, then the properties that they enjoy are similar to the properties of the real part of a complex number. So if you have a complex number and you multiply by a scalar a, and now you ask what's the real part? Well, only when a is positive, you can say that it's true, that you have the a times the real part of the complex number. But in general, if the number you multiply is negative, you don't know what's happening. If you have two complex numbers and you sum them together, it is true that their real part is upper bounded by the sum of their parts equal in the particular. If you translate it by a scalar a, the scalar a will come out. And if the complex number is negative, then okay, I'm gonna skip the differentiation again. Same properties hold for the one-sided Lipschitz expression. All right, I wanted to kind of show to you how these analogies work, and re-emphasize the fact that really ultimately, if you want to apply it in applications, you need to kind of go back and study the linear algebra of induced norms and induced log norms. So right now, I would like to, I've spoken for 45 minutes. I would like to give you an idea of what's in chapter 2 of the lecture notes. I'm not going to go through all of it right now because it would be an hour and a half, and it would be a little bit boring to just study property after property after property. So I'm just going to mention the properties, and then as we work out the examples, if I need to, I'm going to go back and explain the properties in more detail. So here what I did is crazy. I cut and pasted each of the critical lemmas and theorems in the book, and I'm going to show you one at a time. So here's one lemma. So I've shown to you one norm, two norm, infinity norm. If you have a weight, which is a square invertible matrix, you can define the weighted norm. So first of all, if you have a norm, I guess I need to define, let me just do this. If I have a norm, given a norm and the square invertible matrix R, I can define a new norm, which is the weighted norm of X by R, which is just Rx. So this is the norm, right? And this is R. So you give me the norm and R, I can define the weighted norm. So Now, one idea is that if you have the induced norm for the weighted norm, that's the way R from the side, similarity transformation, and the same is true for the log norm. Let's do. How do you do the calculations? Now, this is a little bit more complicated, and I'm not going to be able to make a lot of sense of it. But in network systems, which I will get to probably tomorrow morning, we will have a problem where on the nodes of a graph, at each node, I have a dynamical system, and I define a norm at each node. So I have n nodes. I have norm 1. Now I'm going to say norm 1, norm 2, norm 3. I do not mean to say that's the one norm. I mean to say the norm for agent 1, the norm for agent 2, the norm for agent 3. Whatever the norms are, I don't want to say. Maybe I should call it alpha, beta, gamma, just so that we use a different set of indices. So if you have now, what is the state space of your entire system? Yeah, it's the Cartesian product, the state of the first agent, the state of the second agent, the state of the third agent, and so forth, right? So if you have norms defined for each state, for each substate, then you can define something called a composite norm by taking, you could take, for example, you could take, suppose you have two systems, x1 and x2, and then you take the one norm of x1 and the two norm of x2. Again, this 1 and 2 are not the L1 and L2 norms. It's just for the, maybe I should have said alpha and beta. There, alpha, beta, alpha, alpha, beta, beta. Now that's incredibly hard to read. You can take the norm of x alpha, x beta, a composite norm, to be a norm aggregating the norm of x alpha and the norm of x beta. Does that make sense? So you can construct a norm on the Cartesian product space by combining norms, aggregating norms in each of the subspaces. And when you do that, there is a theorem that tells you how do you make this work and what are bounds that you get for the induced norm at each state, the worst case of that, the induced norm for the composed matrix, and a simplified version of the norm. All right. Third property. The third property, I'm going to show you a picture for because that is just too easy and much more fun rather than trying to do it like that. So let me make sure I don't say something silly. Yes. The spectrum norm and spectrum log norm property. So you've already seen this. The spectrum is included in the spectral radius, and the spectral radius is upper bounded by the induced norm. And that gap is a norm inefficiency. So if you want to write equations, you can say that for any eigenvalue lambda, this holds. 0 is the lower bound on the absolute part. The modulus of lambda, which is upper bounded by the spectral radius of the matrix, which is upper bounded by the induced norm. Now it turns out that if the matrix is invertible, you can actually improve about the 0 there, and you can put 1 over the induced norm of A inverse. All right, good. And just like you have that chain of inequalities for the modulus of the eigenvalue of the matrix. No, sorry. Yeah. You also have a plot that describes, and these are going to be inequalities about the real parts of the eigenvalues. Right? So in blue is the spectrum. The spectrum may have an eigenvalue with the smallest real part and an eigenvalue with the largest real part. The eigenvalue with the largest real part is referred to as the spectrum of C cells. We discussed this later. lambda is an arbitrary eigenvalue in the spectrum of A. Now, the log norm is an upper bound on alpha. So this is the log norm. It's an upper bound on alpha. That's perhaps the key inequality. The key inequality really is that alpha of A is upper bounded by mu of A. Somewhere I read, but I haven't been able to prove it, that the log norm is the smallest convex function of A that upper bounds the spectral CISA, which is not convex, but I don't know how to prove it. So now this gap here is the logarithmic inefficiency. Now I'm going to add more things in this plot. It turns out that the log norm is always upper bounded by the induced norm. So if you're here, the induced norm is always worse, which is to say larger. Why do I say worse? Because oftentimes you would like to show that your system is nice and stable, everything is converging very quickly. So you would like to show that the mu of A is as left as possible, identical to alpha of A, and you hope that your system is stable, right? So you put alpha on the left. Okay. But mu of A is always positive. Pardon. The induced norm of A is always positive of 0, whereas the log norm of A can easily be negative. I mean, for example, I didn't show you an example of this, but the log norm of minus identity is always equal to -1 in any dimension with respect to any norm. You can prove this relatively easily. Now, but you may be interested in also knowing what happens on the other side of the plot. So the smallest real part of the eigenvalues is an upper bound on minus the log norm of -A. And this is itself lower bounded, but minus the induced norm of A. So if you want to, okay. So a nice chains of inequalities, which sometimes could be handy, just to make sure you understand it. And that's what this chain of inequality is here. Okay. Something special happens when the norm has the property of being monotonic and the matrix A is diagonal. I'm going to skip that. And then we have important and useful monotonicity properties. So these are again chains of inequalities. It goes like, first there is the discrete time versions, and then there are the continuous time versions. First, there's the version for the non-convex spectral radius, and then there are the versions for the convex induced norms. Does that make sense? So that's why there are 4. So the spectral radius of A is upper. Can you guys read in the back, or is it too low resolution? This is my fault. This is my fault. 2.24. This is my fault. It's a lack of imagination. It's because of a lack of imagination. So, first inequality, spectral radius. We're in discrete time. Let's do it for the true number that sometimes we find hard to compute, which is the spectral radius. The spectral radius of A is upper bounded by the spectral radius of the absolute value of A, which entry-wise. Remember, we said this earlier. If you were to add any non-negative matrix P to the absolute value of A, it only gets worse. You only get worse, but sometimes, remember, sometimes, why is this useful? Because sometimes A is the Jacobian of a nonlinear system. And maybe if you take absolute value and you upper bound some things, you keep doing upper bound, and in the end, you show that the spectral radius is less than 1, you improve stability. Now, I didn't say it right. I did not say it right. It is not true. It is not true that if the spectral radius of a nonlinear map is less than 1 everywhere in space, that the nonlinear map is stable. It is true, using contraction theory, precisely what we discussed today, that if the induced norm of the Jacobian is less than 1 everywhere in space, that's the Lipschitz constant of the map, it's less than 1, it's a contraction. Just checking the eigenvalues of a discrete time or continuous time nonlinear system is not enough. It's not enough. So I made a very Keep mistake 2 seconds back. So now, I know this is hard to read. Here I meant to say the absolute value of A, and then I take the induced norm. I know there are 3 parallel bars. What is that? Well, first the absolute value, and then the induced norm. So the induced norm of A is upper bounded by the induced norm of the absolute value of A, and if you add no negative terms to it, you're fine. Okay? Those were in discrete time, and in continuous time, they're the same. However, I need to define the symbol. I need to define a symbol. So you should know, before I define it, that there is a magical set of matrices. This magical set of matrices is called the set of Metzler matrices. Metzler matrices have magical properties. And before I show you the properties, let me tell you what's a Metzler matrix. So M in R n times n is Metzler if Mij is greater than or equal to 0 for all I different from J. So pictorially, I have a square matrix. I know nothing about the main diagonal, but outside the main diagonal, I only have pluses or zeros. Does that make sense? That's a Metzler matrix. They're very simple. It's a non-negative off diagonal. Non-negative off diagonal. There are a whole sets of theorems just about Metzler matrices. Now, to be honest, this is the continuous time version of non-negative matrices. So you could start with P. No, let's not use P. Let's use N is positive when basically Nij is greater or equal to 0 for all I and J. And so this is the discrete time case. And that's the continuous time. And essentially, for every property of a Metzler matrix, there is a property of a positive matrix and vice versa. There is a book by Berman and Clemens entitled Positive Matrices or Positive Systems. Non-negative. Good point. And they have a theorem where they give 56 equivalent properties of non-negative matrices that are essentially sure-stable, or 56 equivalent properties of Metzler matrices that are proof. So it's absolute madness. Absolute madness. I'm going to show you some of them, a selection of the ones that are most important. The point is that if you give me an arbitrary matrix A and I take the absolute value of A, I get a non-negative matrix. If you give me an arbitrary matrix A, I wish to define the Metzler absolute value of A. And by that, I mean to say the very simple operation of taking the absolute value only off diagonal, off the main diagonal. Does that make sense? So when I write this M here, absolute value M, I mean to say, please take the absolute value only of the entries off of the main diagonal. Okay? By the way, we have done something like this earlier today. I hope you did not forget about it. Let me remind you when we did that. We did that when we were defining log norms. Here's what we did. When we defined the one norm, we said it is the maximum column sum after you take the absolute value, right? And when we define the one log norm, it's the maximum column sum after you take the absolute value off diagonal. Off diagonal. So, by the way, if you think about those two, and this is true for one and infinity, if you think about those two formulas for one more second, you realize that obviously that the one norm of A is equal to the one norm of the absolute value of A, right? Isn't it? Because when I compute the one norm, the induced one norm of the matrix, first I take the absolute value, and then I do something else, which is the maximum column sum. So really, it's the same. If I look at these two things, must be the same, right? And I'll write it at the top so it's easier to read. And the one, or infinity for that matter, let's write infinity, log norm of A is equal to the infinity log norm of the Metzler absolute value, or people sometimes call it majorant. The Metzler absolute value of A. Why is that true? Because when you think, because you see, this formula depends only upon the absolute value of the off-diagonal entities. Okay. So we are back to my theorem. The theorem says that for the non-convex spectral abscissa, which in any case does not tell you about stability really for a nonlinear system, alpha of A is upper bounded by alpha of the Metzler majorant of A. And if you add no negative terms, you're fine. You're only making it more and more positive. And that's true for both alpha and for mu being the log norm. In fact, what I just showed to you is that if you're working with a one or infinity norm, this sign here is an equality, the strict equality. These are useful in examples because, as I said, you take a Jacobian and you will have some terms and you just upper bound them by something positive. And if you show that what you're left with has negative log norm, well, then for sure also your system has negative log norm, right? Perfect. I think by now you are sick and tired of me, and I am going to take a 5-minute break. Thank you. I will pause recording. Zoom recording. Welcome back after the break. We are recording. Yes. So I have invested a little bit of time of telling you that if you know norms, induced log norms for 1, 2, and infinity norms, then you can also apply weights. And these are the formulas given this equation 2.34. We then saw these composite norms. There's a theorem about that, which will be closely related to the interconnection of contracting systems. Then we've seen that when you look at the spectrum and these induced log norms, you have these plots telling you what's smaller and how do you make it larger. And kind of related to that is other inequalities that have to do with monotonicity properties. So it all really kind of, once you put your mind to it, all of these little, it's like Lego pieces. They all fit together quite nicely. Now, in the chapter, I then have a whole bunch of results, actually precisely 4, which I'm going to skip right now, and I will get to when I need them, on the following topic. Given a matrix A, how do I design an optimal norm? More precisely, how do I design a weight such that you give me you say 1 norm or 2 norm? How do you design an optimal weight for the 2 norm or the 1 norm or the infinity norm in such a way that the resulting weighted norm is logarithmically optimal or optimal, or efficient if the dominant eigenvalues are repeated?
You mean efficient with respect to, say, to the gap?
That's right.
The
Exactly. You want to close the gap between the spectral radius and the induced norm, and that's optimality or epsilon optimality or efficiency. Or in continuous time case, you want to close the gap between the spectral abscissa and the log norm. And again, it's it's not true, unfortunately, that an optimal norm exists when the dominant eigenvalues are repeated. And this has to do with the problems that you notice that when you compute the matrix exponential of the matrix with repeated eigenvalues, then you have these evolutions which grow linearly in time before the exponential dominates. Anyway, now, yeah, let me skip this because this itself, these 4 lemmas can take a long time. But just so you know, or I'm gonna do only one thing I want to teach you, which is really kind of cool. It works like I'll just say this one thing right now, which is kind of nice. It's gonna see if you can follow the thought. I have mentioned to you, I've sort of proven it, that this function is convex. Convex. Convex means that, well, you know what convex means, right? It means that alpha A plus alpha 1A plus B. No, let's not do it like that. That's really awkward. A1, no, let's try again. B1A1 plus B2A2 is upper bounded by where B1 and B2 are convex combination coefficients. That means that they are greater than or equal to 0, and B1 plus B2 is equal to 1. This is less than equal than B1 induced norm of A1 plus B2 induced norms of A2, convex. And this is the same is true also for the log norm. With respect to any norm, the log norm is convex in the argument. All right. Now, but what I said to you is that I wish to design optimal weights. So now I'm not, and now what happens is that fix A is fixed. Consider the map R into this map. Now this is a different map, right? Because now, as a function of the weight, you're spitting out an induced norm. This is a scalar, just like before. But now the domain is not the domain of matrices, the domain of weights, right? So when is this map convex? Because I'm going to want to minimize this, because I'm always trying to minimize it. And I hope it's convex so I can find a solution. When is this map convex? And of course, I mean to say both maps. I'm interested in this, and I am interested in that. All right. So it turns out that there are two cases where this map, actually, it turns out that this map is not convex. This map is quasi-convex in two cases, in two useful cases. Does it make sense? What's the quasi-convex map? A quasi-convex map is a map that can have, like a convex function is like a cup. A quasi-convex can be flat and then continue to grow. The inverse level set of a quasi-convex function is always convex. So go study your convex optimization theory in the chapter where convex functions are defined, strongly convex functions are defined, quasi-convex functions are defined. Quasi-convex functions, if you want to minimize quasi-convex, it's not that bad. It's a bisectional algorithm. It still works. And the theorem is that these two functions are quasi-convex, but these are the two cases, right? Case number one, is it large enough? Can you guys see? No, let's go 2.29. Let's go to 2.29 so that I can properly enlarge it. Oh, there's also, I'll show you a numerical example. I was about to forget about that. Yeah, a function is quasi-convex. It's a sub-level set is convex. And a convex function satisfies this property, right? The one that I just wrote, that I B1, B2, or theta 1 minus theta, where theta is a number between 0 and 1. A quasi-convex, this quantity, the convex combination of the argument, is upper bounded by the worst case, either the maximum of fx or fy. That's quasi-convex. Now, here are the two cases. This map is quasi-convex. What is this map? This symbol, I apologize, I wanted to define the domain. This symbol is a new symbol. I mean to say positive definite matrices. This is the set of positive definite matrices. From the set of positive definite matrices, I map that into the log norm of A with respect to the weight P. This is quasi-convex. What this means is that the level set are convex, right? A quasi-convex function has convex level sets. What's the convex level set? It's a set of P that have a certain contraction rate B, and that's the set of P that satisfy this LMI. You already knew that this was a convex set because the set of matrices P that satisfies this LMI is known to be convex. At fixed B, you give me a performance level P and this is convex. And there, in fact, that's why LMIs are studied in convex optimization, because the set of solutions of an LMI is convex. The other result, which is much less famous, is that if you take the set of positive vectors and you map that into the one norm with weight eta, let me just finish. Let me clarify that in a second. Or in the infinity norm, weighted by a vector, then those functions are quasi-convex. And this is also true because of what I had said, earlier today, and that is to say that at the performance level, you can solve these linear programs. And so when you have linear programs, of course, the solutions, the set of vectors eta that satisfy linear inequalities are polyhedral, right? It's the intersection of half planes with the polyhedral. All right, perfect. So these are the only two cases. Any questions on this? So once it's quasi-convex, you can optimize it, and I'll leave it at that.
Those P are more than just the element, right?
P is positive definite. So there's a difference between two. This is arbitrary positive definite matrices, and this is only diagonal positive diagonal matrices with a positive diagonal. It is not true that for the infinity norm or the one norm, you can use positive definite weights, and the optimization of those weights is a convex problem. That is not true, to the best of my knowledge. I don't believe it's true. It's true only when I use, well, basically a diagonal positive definite matrix. Yeah. Okay. All right. I would like to show you some examples before I go back to the mainline nonlinear theory of contracting dynamical systems. So I have defined the concept of contractivity. Actually, to be precise, I've defined the concept of strong contractivity with a strictly positive contraction rate in continuous time for a strictly less than one contraction factor in discrete time. So later on, I say strongly because later on we'll do generalizations where we do weakly contracting or non-expansive systems. And I still owe you a bunch of properties of these contracting systems. I need to tell you what are the Lyapunov functions, what happens, why are they robust with respect to disturbances. I need to tell you why do they entrain to periodic inputs, all sorts of things, right? That I haven't done yet. In slide number 2 earlier today, I told you they have many properties, and I haven't showed to you the properties yet. Before I show you the property, let me show you some examples because it's fun to see the examples. At least, you kind of see the examples before we do some more theory. All right. So let us start with, essentially, I want to talk about gradient dynamics of various types. So this is the first example. So I'll show you many examples that are gradient, primal-dual gradient ascent, gradient ascent, dual descent, distributed gradient. I'll show you many variations on the concept of gradient descent. So I will start by reminding you that there is a concept called strong convexity. So a function is convex if at any point, you take any point, you draw the tangent to the function and the tangent lower bound the function, right? That's convexity. Here, I picked an arbitrary point x and I draw the tangent to it. So it has the same value as the curve and the same angular coefficient as the curve. And it lower bounds the blue curve. So the blue curve is convex. But you can do a little bit better. Here, you can actually draw a parabola. So you can add a quadratic term to your lower bound. And it still remains a lower bound. So you are not, so for example, a line is convex. It is not strongly convex. A parabola is strongly convex, right? It's like a bend. Your lower bound is bending, and yet the function is still above it. And it's this concept of strong convexity is very well known and widely studied in optimization theory, in continuous optimization theory. Now, there are many ways to write down this picture, this property that I have drawn for you with my hands. For example, these three here are known to be equivalent, right? These are equivalent. If you have taken a course on convex optimization, you probably would know this. So I apologize, I'm changing notation. I use B1, B2, then I use theta in a separate slide. Right now I'm using key. Key is a number between 0 and 1. So I take 2 points, x and y. I use a little bit of x and 1 minus that same little bit of y, right? And the function is convex. It's strongly convex when key times f of x, 1 minus key times f of y, is upper bounding the function, but now I'm going to subtract something from the upper bound on the right hand side. So basically, it's even tighter, right? And what is that something? That something is key times 1 minus key, x minus y squared. Look at the square of the norm; it always comes in handy. And then you put here as large a parameter mu as you can. So your function is mu strongly convex. If mu strictly positive, makes this equation come true for all x's and y's. So this is an inequality 1 that uses no derivatives, right? Let's look at this one more time. There is no derivative of the function f in the first definition, right? This is equivalent. Well, I'm going to now give you condition 2 and condition 3, which have to do when the function is differentiable or twice differentiable. When the function is differentiable, you ask precisely this property here that I have illustrated right here, that this quadratic curve lower bounds that, because now you compute the tangent, right? And the tangent, to compute the tangent, you need to compute the gradient of f. And now literally you're saying that well, my picture is wrong. Sorry, this should, x and y are exactly the opposite in the picture. But anyway, imagine that this is. Oh, I can easily fix that in 5 seconds. Are you ready? There. Okay, fine. Y and x. All right. So now, at x, f of x is greater than, start at f of y, move along the line, move along the linear approximation, which is gradient of f of y times x minus y, which is the black curve, and then add a little bit more, add mu halves of the distance between x and y squared, and that gives you the parabola. Does that make sense? Now, so this is condition 1, this is condition 2, this is condition 4, because I don't know how to count, and this is condition 3. I know what. So 2 and 3 are the same, even though it's not obvious at all that they are the same. In fact, it's a 1960s theorem by a Russian optimization mathematician, showing that condition 2 can be rewritten if you basically write this property for x and y, y and x, and manipulate it the proper way. And then you have to go both ways. You need to show that 2 implies 3 and 3 implies 2. So there's a little bit of manipulations. But it turns out that this idea of lower bounding with a parabola can be equally rewritten as, are you ready? Gradient of x minus gradient of y into x minus y, upper bounded by a constant times x minus y squared. Does that remind you of something that we have seen today? It should. And you should say, but Francesco, it's kind of wrong. It should be lower bounded by something negative. Instead, it's upper bounding something positive. And I would say, well, you're right, because we need to multiply by -1. Because we are not doing gradient ascent, we're doing gradient descent. So the vector field that we will be interested in a second, f of x, is going to be the gradient of f at x minus. Minus. So if you multiply that equation 3 by -1, then you're going to get minus. Well, okay, let's with this definition here, right? With the definition up there, this is after I multiply equation 3 by -1, I'm going to get fx minus fy into x minus y less than equal, because when you multiply by -1, the sign of the derivative changes, minus nu, which multiplies x minus y squared. Hence, minus nu, what have I discovered? We have discovered that if I have a differentiable, strongly convex function, minus its gradient has a one-sided Lipschitz constant equal to minus mu, where mu is called the strong convexity parameters. And there is no gap. It's actually if and only if. So there's a minus sign floating around it. It's really annoying. If you want me to, I can talk about strongly concave functions. A differentiable function is strongly concave if and only if its gradient is strongly contracting. It's strongly concave with parameter mu if and only if the gradient is strongly contracting rate mu. So the strong convexity parameter and the contraction rate are the same. And to be clear, one more comment, this is with respect to the 2 norm. So when I say that the gradient descent, that minus the gradient of a strongly convex function is contracting, I mean to say with respect to the 2 norm. With respect to the 2 norm. Unweighted 2 norm. Now, let me show you one more obvious reasons why this is true. The fourth, well, it's the third character. Well, actually, it's the fourth one, really, right? Because I have given you 1, 2, 3. I am not consistent with my own numbering. But in any case, if the scalar function f is twice differentiable, if you can take 2 derivatives, then it is known that the function is convex when the Hessian is positive semi-definite. And the function is strongly convex when the Hessian is lower bounded by the identity times the strong convexity parameter. So the Hessian matrix, the matrix of second order derivatives, it's symmetric. It has therefore real eigenvalues. You want all of those eigenvalues to be strictly positive. The smallest of them also over x, right? This must hold for all x's, is mu. That's the strong convexity parameter for you. And the Hessian is symmetrical. Let's remember that. Okay, so here's in summary what have we learned so far. We have learned that I'd like to take a function f, a scalar function from Rn to R. I need to make it differentiable, otherwise I cannot define the gradient descent, right? Although I could weaken the differentiability assumption. For now, later in the week, I will weaken that. I'm going to study strongly convex functions. So they're very well behaved. An example of a strongly convex function, a canonical one, of course, is you give me a positive definite matrix Q equal to Q transpose positive definite. F of x could be X transpose QX. Okay, that's the canonical strongly convex function. But really, you can accommodate all sorts of nonlinearity, so long as the Hessian is lower bounded by a positive definite. All right, lots of words. So here, I'm going to define the gradient descent vector field f sub g minus nabla f of x. My function is strongly convex with parameter mu. Again, just for you to remember, sometimes people write strongly convex with parameter mu. Sometimes people just write mu strongly. It's just because if you read one or the other, maybe you're confused. It's the same. So then the theorem is that Fg is infinitesimally strongly contracting with respect to the standard, the 2 norm with the rate mu. And what does that mean? Of course, like we already knew that, there exists, well, if it's strongly convex, it has a unique global minimum. This is known from optimization. And in fact, it is going to be true. I haven't shown to you the, no, I actually, that's part of the Banach contraction theorem for continuous time dynamical system. So from the continuous time Banach contraction theorem, we know that this dynamical system has unique, globally exponentially stable equilibrium point. And the rate of convergence is the strong convexity parameter. Any questions? This is the first example, the canonical example. Super simple. Why is this true? I am going to give you I'm going to give you a proof, which is very simple. The reason it's true is because of this equality here between 2 and 3, but I did not prove it. Let me give you a different proof that works for functions that are twice differentiable. So it's not needed to assume twice differentiability, but the proof becomes so easy that I can do it in one line. So let me do that in one line. Now, here, it's really complicated just to read the symbols, but the proof is trivial. It goes like this. Suppose you're twice differentiable. Now you know that the Hessian is lower bounded by mu times identity. But the Hessian of the function, if you go back to your calculus book, is equal to the Jacobian of the gradient. Now there is a minus sign floating around, right? So if I write Hessian or if I write Jacobian of the gradient, it's the same thing. There's a minus sign. Whether you put the minus sign out there, here, inside F, it doesn't matter, right? So I have a minus sign here, I have a minus sign there. That's the only thing. So now the Jacobian of the vector field is equal to the Hessian, the minus sign. Now I had greater than equal than plus mu. Now it becomes less than equal than minus mu. Right hand side and left hand side are symmetric. But if the left hand side is symmetric, I can sum two copies of the left hand side. One is going to be the left hand side, and the other one is going to be the transpose. I may do that, right? I take the left hand side. This is the left hand side, and this is the left hand side transpose. And then I multiply them both by the identity matrix. Here's the identity matrix, and here's the identity matrix. And that has to be upper bounded by minus 2 mu identity. Does this make sense? I hope I did not trick you. It's just a slow rewriting. What have I obtained here? I have obtained my contractivity LMI, haven't I? Because now this is P dF plus dF transpose P is less than equal than minus 2 mu P, where P is equal to the identity. And dF it's equal to d of minus the gradient of f, which is equal to minus the Hessian of f. Does that make sense? So really what is happening here is that the key idea is that the Jacobian of the gradient is the Hessian, and if the Hessian was negative definite, then the Jacobian of the gradient is going to be negative definite, and a negative definite matrix has log norm that is negative. The negative definite matrix has a log norm that is negative. Maybe I should show you that. Let us just think about that for one more second. No. Here it is. Suppose that I give you a matrix A that is negative definite. If A is negative definite, asymmetric. So A plus A transpose is equal to 2A divided by 2. So A plus A transpose divided by 2 is A. Lambda max of a negative definite matrix is negative, because if it's negative definite, all of the eigenvalues are negative. It's the largest eigenvalue, but it's going to be negative. All right, fine. That was my first example for today. Next.
Easy also to show the other two norms.
The other two norms.
Take L1 or everything norms. Would that be an easy way to characterize it?
Actually, this is a great question, because now what Professor Altvin is hinting at is I have a strongly convex function and it's strongly contracting with respect to the two norm. What if I take a function, I have a strongly convex function and minus its gradient is strongly contracting with respect to the two norm. What if I were to ask for that minus the gradient to be strongly contracting with respect to another norm? What does the function need to be in order for its gradient to be strongly contracting with respect to the other norm? So I am going to give you an exercise on this. For those of you who wish to, I will just say one thing to clarify, and it's the following. If well, okay, let me just tell you the answer. If A is equal to, I'm just going to tell you an algebraic fact, and then you can use it to draw some conclusions. If A is equal to A transpose, like for example for positive definite, negative definite, just symmetric, then the 2 log norm of A, it's equal to lambda max of A plus A transpose over 2, but that's just equal to lambda max of A, right? Because A is equal to it. The next thing is that if A is symmetric, we all know that all of the eigenvalues are real. We know that the largest eigenvalue, well, what has happened? What has happened is now that the large eigenvalue has 2 names. I have called the largest eigenvalue alpha of A, which is the spectral abscissa of A, but also it's lambda max of A, because lambda, remember, lambda max or is defined only for symmetric matrices. If you give me an asymmetric matrix, I cannot talk about lambda max because that I can talk about the spectral abscissa. So this is equal to alpha of A. In the inequalities that we had seen before, we had learned that alpha of A is less than equal than mu of A for every norm. But here, what I have proved for you very, very simply, it's just a matter of notation almost, that when the matrix is symmetric, the 2 norm is logarithmically optimal. Logarithmically optimal means there exists no gap between the spectral abscissa and the log norm. They are identical. Does that make sense? I'll let you prove that the 2 norm is also optimal without the logarithmic for symmetric matrices. And I am going to make the blanket statement that this algebraic fact provides an answer to what Professor Ottini asked us. But I'll let you think about that. All right. For those of you who are interested, the original proof was by Kaczorowski in 1960, and there is an entire field of optimization called monotone operator theory. And I just want to make the case that if you ever encounter a monotone operator in monotone operator theory, it's exactly the same as minus a strongly contracting vector field. So just to clarify that, unfortunately, there's a lot of language in the literature, which at the end of the day is equivalent. All right, now, if time allows, I would like to talk about example number 2. Example number 2 goes like this. Suppose that I do have a strongly convex function f, and I do want to minimize it. However, I have a constraint now. I have a linear equality constraint. There are also linear inequality constraints, which are quite important. I may not have time to deal with them. Now, I have a linearly constrained optimization problem for a strongly convex function. So you have a strongly convex function, but the linear constraint is going to give you an affine subspace. And essentially, it's still, your optimization problem is still going to have a unique global optimum, just in case you wonder from optimization theory, we sort of know that. So now, this problem was studied long ago by economists called Arrow and Hurwicz, and in the 1950s or 60s, and they wrote a dynamical system. At that time, digital computers weren't as widespread as they are now, and they wrote a continuous time differential equation to solve the linearly constrained optimization problem, which is this one here. The full story, I could spend a lot of time talking about the fact that they take this and they write they take of lambda's Lagrange multiplier, it's the dual variable, they write the Lagrangian function, and they write the conditions. I'm going to skip that in the interest of time, because I don't need it in what follows. And if you're interested in optimization, you can go study it. Now, but the point is that it's just a name for all that this course is concerned, is that you are going to define something called the primal dual gradient dynamics, you introduce variables lambda. You have as many variable lambda, so X lives in Rn. And then if B lives in Rm, that means that lambda, the dual variables, are going to live in Rm. There will be M dual variables, right? And then the matrix A here is not square. It's a rectangle. Now it's n times n, right? Something like that. M times n. And it turns out that Hurwicz and Arrow suggest using this dynamical system. And they claim that when you let time go to infinity, lambda will converge to something, and X will converge to the solution of your linearly constrained optimization problem under some conditions on F and A, which we need to discuss. So here I'm going to make a couple more assumptions. So I'm going to assume that the Hessian of F is lower bounded by a strong convexity parameter, mu. But because I'm going to have also an upper bound, I'm going to call mu minimum the strong convexity parameter, and mu maximum is going to be an upper bound on the Hessian. Does that make sense? People call this sometimes strong smoothness assumption. So the Hessian is a positive definite matrix. It can become very small, it can become very large, but it is upper and lower bounded by mu minimum and mu maximum times the identity. So the eigenvalues of the Hessian are functions of the state, but they assume a minimum and a maximum value. Does that make sense? All right. So I have defined two parameters, mu minimum, which is clearly less than equal than mu maximum. Also, the next thing is the constraint matrix. So I'm going to make an assumption now, which in fact is not needed, but let me make it for now because the assumption is that when you look at these constraints, these equality constraints, none of them is redundant. They are all needed. And what that means is that the matrix A has linearly independent rows. Each row is a linearly independent vector from the other. You have a family of vectors which are linearly independent. And so what that means in turn is that if you calculate A transpose, now you get a square matrix. And this square matrix is going to be positive definite because the rows were independent. And here I have, by the way, here I have fewer constraints. M is less than N. If I have more constraints, then they cannot be linearly independent, by the way, right? Because you have N plus 1 constraints on N variables, they're going to have to be linearly dependent, right? You have N plus 1 vectors in dimension N, it's not possible, right? So and also because if I have too many constraints, then here I don't have any optimization problem, right? I mean, I have N variables and I have fewer sets of constraints, right? All right. And this A transpose is full rank, right? So it becomes a square matrix. It's invertible, so it's a symmetric matrix. And again, it's positive definite. And I'm gonna let A mean and A max denote those two bounds. Does that make sense? Any question? So the existence of A mean A max follows from the independent rows assumption. All right. So the statement is that even this dynamical system, the Hurwicz-Arrow primal-dual gradient flow, is infinitesimally strongly contracting. Well, it's not a surprise because this is the mini course of contraction theory, so it would be quite surprising if it was not contracting. Claiming that the slide is called example number 2, right? It is contracting, but not with respect to the unweighted 2 norm. It is contracting with respect to a weighted 2 norm. I need to define a weight matrix, a P positive definite matrix. And this P matrix has a certain shape, which I would like to illustrate for you. It's identity in n dimensions, identity in m dimensions, and then I have A and A transpose. So that if you just write down the dimensions of A, which is m times n, this will make sense dimensionally. This will be a n plus m square matrix P. Now you should ask me, Francesco, what is alpha here? You have a parameter. alpha is defined like that. It's 1/2, the smallest of two numbers, 1 over nu max, nu min over A max. The four parameters are nu min, nu max, A min, A max. So there are four parameters in the problem, and you use three of them in this particular way. And the next thing you should ask me is, Francesco, what's the contraction rate? Because I want to know the norm with respect to which you're contracting and the rates at which you're contracting. And right now, the rate I have is a coefficient 1/4, which multiplies the scaled version of this minimum. It's scaled by multiplying A min. Does that make sense? Now, this results, so in the previous slide, in example 1, the strong convexity parameter, well, sometimes you don't know the exact strong convexity parameter. You have an estimate for the strong convexity. You know that a certain parameter works. Maybe the real convexity parameter is larger. So whenever I tell you that my system is contracting with the given rates, unless I tell you that is the optimal rate for sure, it's just an estimate of the rate. Maybe the rate is faster, it's much faster. So I'm telling you, I'm sharing with you this information, this rate, this estimate of the rate is conservative. So the actual rate is going to be larger than that. The rate of convergence is going to be, the contractivity rate is larger than that. But this, for sure, this combination of this P with the alpha here and that C work. What do I mean to say they work? I mean to say that together they satisfy. So how do I check that I have contractivity? How do I check that I have contractivity? The way I check it is I take the Jacobian of F Primal-dual. I know that part of it is going to have to do with a Hessian. And in particular, this Jacobian is going to look like this matrix here that I have here at the bottom. Can you guys read in the back? So this matrix here, minus Q minus A transpose A0 is equal to the, well, is related to the Jacobian of the Primal-dual flow with the following characteristic. Q is an arbitrary matrix that it's varying in a certain range, and the range is mu min identity inside mu max identity. So this Jacobian is always going to fit in this collection of matrices where Q varies in that set. And how do I prove contractivity with respect to a weighted two norm? Oh, that's very, well, potentially it's very easy. I need to satisfy a linear matrix inequality, which is the state matrix, in this case it's this beast here, times P, well, state matrix transpose P plus P state matrix less than or equal to minus 2 contraction rate and then P matrix again. Does that make sense? So to prove contractivity, if I wanted to prove for you this particular statement here, my claim that the Hurwitz-Harrow Primal-dual gradient descent is strongly contracting with that rate with respect to this norm, I only need to verify this linear matrix inequality. Does that make sense? So it's an algebraic problem now. I just need to fight against this LMI. I don't think we want to fight against this LMI today. Let us tackle this LMI tomorrow. How tired are you? I think you look tired. You look tired. So I'm gonna stop here. But I will warn you that LMIs can be tricky animals. Okay. They're not like the beautiful magic Metzler matrices. No. LMIs are just what they are. So tomorrow I will give you a glimpse in how do you prove these more complex facts. And also this is example number 2. I think I have 8 or 9 examples that will follow, but this one is kind of a critical one. So any questions at this time? Yeah. Yes, but also when I select the optimal norm, I may get a larger contraction rate. And the contraction rate is how much can I push to the left? I cannot push it past the spectral abscissa. Now here, this is a state-dependent Jacobian, right? So I have a state-dependent Jacobian, and at every point in space, the spectral abscissas may be changing, and I am finding an upper bound C, well, minus C, that works for everywhere in space. But it is not just an upper bound on the spectral abscissa. It is the solution of an LMI, which is providing to you a lot of structure, well, the contractivity structure, which tomorrow we'll see what it implies. Yeah. Of course.
Why is it I don't know the name.
Why the name? What is the motivation for the name? I think that's an excellent question. And now we need to surmise what it is that Sergei Lodzinski in 1958 and Charlie Dissauer, Vidyasagar in the early 70s, and finally, what was it that Dahlquist decided in 1976? So the history is tricky. So Lodzinski called it logarithmic norm. And I don't love the name because it's not a norm, but at least it says logarithmic norm. In control theory, you have heard of this concept called a Lyapunov function, right? And then if you have a control signal, you may have heard of the concept called a control Lyapunov function. A control Lyapunov function is not a Lyapunov function. Is that still the name control Lyapunov in graph theory? There's the Laplacian matrix, and then people have defined something that is called the edge Laplacian matrix. Have you heard of the edge Laplacian matrix? The edge Laplacian matrix is not a Laplacian. So, but it is surprising, right? If you first time you hear edge Laplacian, it's like it's not a Laplacian. Why are you calling it Laplacian? So I don't know what to tell you. I could give it a brand new name if you want me to. It's just that I do. So this nomenclature. So it's the fact that the problem is even worse. So Lodzinski called it logarithmic norm in Cyrillic in 1958. I don't know when Western scientists read that. Dahlquist, in his PhD thesis, used the symbol mu in 1958. So Vidyasagar and Charlie Dissauer saw the symbol mu and started to call that operation the matrix measure. So in fact, there are two names for log norm. One is called matrix measure, the other is called log norm. Among the two names, they're both evils. I selected the lesser of the two evils because the log norm is for sure not a measure. A measure, as in measure theory, is very well defined, and the log norm ain't a measure. And if you say matrix measure, what I understand is a measure of a set of matrices, which it is not. So with all due respect, I don't think we should be calling it a matrix measure. But this happened because Dahlquist in 58 used the symbol mu and gave it no name. So now I have a joke. So you see, in some religions, when the baby is born, you have to baptize the baby. So the concept is, if you define a mathematical quantity in your papers, in your research, think carefully about what to call it. Choose a good name and choose a good symbol for it. Okay, and if you don't do that, then 50 years later, no, 58, 50, or sorry, my arithmetics is difficult. 65 years later, people are asking you this type of questions. And you're right, it's why do you use mu? And in fact, I kind of hinted at that, which is, if you look at this table, really what you should tell me is, Francesco, you don't know mathematics. How do you possibly put a table like this out? You really should not dare to use four almost completely different symbols for quantities that are very related to each other. symbols and names. So if this is the matrix norm, these are called log norms. Okay, this log should tell you it's not a norm. And then why are you using mu when that was a 2 bar? Shouldn't I use like 3 bars or a bar with a strike or something that tells you that they're similar? No, this is completely different. On top of that, if I have a weighted norm, people write the weighted induced norm of A like that. But if you write mu of A, they put the R there, which is, you know, like mathematics is based upon symmetries and parallelisms, and this does not have it at all. And then, okay, this is called the Lipschitz constant. And then in 1976, Dahlquist called that the one-sided Lipschitz constant. But shouldn't I call this the log Lipschitz constant? Because if that was the log norm, now this should be the log Lipschitz constant. Anyway, one thing I can tell you, my book is written with LaTeX/new commands definition, so I can change it all in just 1 second. We can change the names, the symbols, everything. But anyway, so log norm is not a norm. It has different properties. It has the properties of the real part of a complex number rather than.
What's logarithmic about?
The definition hints at the logarithm because it's -1 divided by h. Let me, I don't know. No, I know it's got to do. Why is it called the log? Because no. Give me 1 tiny extra second. Did I write it here? Or did I forget to write it? I don't have it here. Because I'll bring it to you tomorrow. Because if you take the derivative with respect to time of the logarithm of the norm of the solution to a linear system, e to the at, then you get precisely that this is upper bounded by the log norm of A, and you evaluate it equal to 0, something like that. A formula like that, when you apply the logarithm to the norm, and you take, it's upper bounded by the log. So some formula like that is not so critical right now. Yeah. We're staying for dinner, right, Claudio? The delivery.
So is every two-stable matrix a contracting system? So if I have extra
Every linear system? Yes. Probably. I think I may have made a mistake. Well, that has to do with the optimal. So maybe I'll try to clarify that tomorrow. But I should have had the linear systems cases here, maybe as example 0 in discrete and continuous time. So if your matrix is sure, that means the spectral radius is less than 1. I need to go look for an optimal norm or an efficient norm that gets really close to the spectral radius. So if I find any norm such that the induced norm of A is equal to the spectral radius, then I would like to insist there is no transient, the decay is exponentially fast with respect to that norm. If you use a different norm, you will see overshoot and then decrease. So allow me to show you one picture. Pictures are fun, right? You guys don't hate me too much if I show you a picture. Here's the last picture, and then we go. It goes like this. The blue lines on the right are the same as on the left. Well, that's not true. There are more blue lines here than there, but all the blue lines here are equal to the ones that are there. So what are you observing here? You are observing two spheres, right? 2 circles. These are, imagine that your equilibrium point is at the origin, and here you have a contracting system with respect to the 2 norm. So every initial condition at distance 1 from the origin in the 2 norm contracts and goes inside, and after a certain amount of time, if you tell me that you want to be 0.7 of the initial value, then all of these trajectories go inside, right? You see that, right? This curve goes inside, that curve, all of the conditions go strictly inside. Does that make sense? And monotonically so. Monotonically so. So here, if I shrink it just a tiny bit or a tiny bit more, it's all going inside monotonically. Now, suppose that you use the wrong norm. So here I'm using the one norm to try to see if by any chance the one norm is decreasing. Okay? So, but the system is contracting with respect to the two norm, not the one norm. So what is the behavior that you expect to see? Here's the behavior that you expect to see. And let's pick one particular initial condition, which is particularly useful. So now notice that this condition belongs to both unit disks. It belongs to the unit disk for the two norm, which is a circle, and the unit disk for the one norm, which is a diamond, right? In the two norm, the trajectory goes strictly inside immediately, and it keeps shrinking in the two norm, right? This is the red curve. In fact, in the end, it's going to end up inside any disk, any circular disk as small as you want it to. But now think about it in terms of the one norm. The one norm was equal to 1 here, but then it immediately becomes larger, doesn't it? Because now this curve is going outside of the one of the unit ball of the one norm. So now your one norm is larger than 1, right? And then as you keep flying here, as you keep flowing, your one norm is still larger than 1. Okay, sorry. Here, it's equal to 1. So now you think, oh, maybe now it's going to be monotonic. That's not true. So for example, here it goes into a smaller diamond, but then it goes out, right? And yes, it is true that in the end, you're going to end up inside the smaller one norm here. This is, anyway. So if you look at the evolution of the contracting system with respect to the wrong norm, it is not true that it is decreasing. The norms are equivalent, but that does not mean you have lost the monotonicity. It is still true that you are converging to the equilibrium point exponentially fast, but you could be oscillating. There could be a large transient. All right. Thank you all. I shall see you tomorrow morning.